So the trends that we exploit really come from how electrons are arranged. So when you do the graph, and it talked about what's common about the atomic structure of the peakiest peaks and the most deepest valleys, what you'll notice is the peakiest peaks are the same type of elements, and then the most, or they're in the same group, and then the valley has the same type of elements based on, which is important for their atomic structure. How many valence electrons do they have? How many Bohr-Rutherford or how many shells or energy levels are in their Bohr-Rutherford diagram? So we'll define first electron repulsion and what nuclear charge is. So, you know, a cheesy analogy is the chemistry between two people, right? Do you attract or do you repel? And I really think it comes from this. Electrons have the same charge, they attract, that's chemistry. Or sorry, they repel, that's chemistry. And then the nucleus has a charge that's positive. So that means that they're going to attract and not repel, okay? That's chemistry. I believe the stuff you have to fill in is yellow. Yes? Again, I chose this one. It's all capitals. If you don't like to write in capitals, don't feel like you have to. Okay, so electrons have negative charges, like charges repel. So it says, therefore, electrons try to orient themselves. So you have to kind of think 3D. How are the electrons arranged? They are arranged as far apart as possible. We talked a little bit about this when I reviewed Lewis structures, that we don't draw the symbol with all 5 valence electrons, let's say, all stuck together, because that does not happen. They try to be as far apart as they possibly can. So as far apart as they possibly can, but also as close to the positiveness in the nucleus as they can be. So the next slide says nuclear charge. It doesn't mean, it's an unfortunate term, nuclear. It doesn't mean like nuclear bomb. What it means is literally the charge inside the nucleus. So in the nucleus, there are protons, which are positive, and neutrons are neutral. So then the nuclear charge is how many protons there are, or the atomic number. So because we deal with relative charge plus 1 minus 1, then we can look at how many protons there are compared to the number of electrons. Okay, so we are going to look at, if you could see if you look at the next two, there's those weird diagrams there. We're going to look at what happens when you go up and down the periodic table and when you go across. Because we are English readers, we usually consider the trends from starting at the left, moving to the right, but you don't have to. So that's what we're going to do. So when you go up and down, then that means that you increase the number of energy shells, which literally, you can literally think of it like, again, an unfortunate analogy. If you add weight to something, it gets fatter, it gets bigger, right? Actually, so when you add energy shells, that obviously makes the atom larger. So row number 1 has 1 shell, row number 2 would have 2, row number 3 would have 3, etc. We already talked about that. And another thing happens. So not only does the atom get larger, which is then going to affect, we're going to talk about the energy required to remove an electron from an atom. You guys drew a graph about the size, the radius of an atom. So what happens to the atom as you go down? It's going to get larger because there are more rows. But another thing also occurs. So when you go down, that's a powerful trend compared to across, okay? Because once you get more shells, these shells inside here, and one of the reasons I kind of like this representation of an atom, because they literally look like shields. So what happens is, not only is it larger, just because you're gaining more electrons and shells, but also now these outer electrons are, we call it shielded from the nucleus. The nucleus is positive, electrons like positiveness, but they can't feel it as well because these shields are getting in the way. So this looks like shield, shield. These outer electrons then are already far away because it's big, and now they're extra far away because they're also shielded. So they are not held as tightly to the nucleus. So if you want to add that to your picture, that these two rows, these two energy shells now act as shields. Okay, so then when you go across, you are not going to get any more shells, but the positiveness inside the nucleus increases. So now we're dealing with only one row. So row number one has one proton, and then helium number two has two, and so on, okay? So, and then you would consider, so hydrogen and helium, you would consider them, like you could rank them, and then you would look at the next row, lithium, beryllium, boron, carbon, because they would have the same number of shells. So what happens if you're not getting more shells, but you're getting more positiveness? So then you will, you can literally think of it like holding hands. If you hold one hand, then the person can move around. If you hold two hands, then you can pull them in closer, okay? So once you have more positiveness in the nucleus, the electrons are attracted to that, making the atom tighter. So that makes it smaller, and that's going to influence making it an ion, removing electrons, that kind of thing. I think you have both. Okay. So then this picture down here has two protons, two electrons, and the space between the shell and the nucleus is on purpose smaller.